Welcome to the third video of Chapter 20 of Crystal Clear Electronics 2. In this part, we will talk about how we can measure and estimate the current consumption of a microcontroller.
For example, you can measure the current consumption of the microcontroller by itself. To do this, first convert the current into a voltage, and then we can process this signal using the ADC described in Chapter 11. The procedure is based on inserting a small resistor, shunt, into the current path, the value of which is known exactly. The more precisely we know the value of our resistance, the more accurately we can calculate the current we want to measure. In fact, it is essential to take into account the tolerance of the component, which determines the range within which the actual resistance can vary from its nominal value. Generally speaking, it's advisable to choose a resistor with a tolerance of 1%, or an even smaller percent is better for this purpose. However, the current consumption of our microcontroller is so small, only a few 10 mA range, that an operational amplifier-based measurement circuit and a sufficiently high-resolution ADC are required to accurately measure the voltage across the resistor. In the upcoming video part, we will use a multimeter for simplicity to measure the consumption of the microcontroller. The instrument uses a shunt resistor-based measurement.
Now that we are talking about measurements, I find it important to mention the methods based on the measuring coil and the Hall effect. Can you help me with this?
Sure, let's talk a little bit about these also. By using a coil, we are able to measure alternating current in the wires. For example, it can be found in instruments designed to measure high current cables. In this case, the main advantage of the method over shunt resistance-based measurement is that it does not require the circuit to be disassembled and the dissipative component to be installed. In Hall effect measurement, a current-carrying conductor plate is placed in a magnetic field, and the resulting Lorentz force causes charge separation. The sensor measures the potential difference between the separated charges, which is proportional to the current flowing through. The method is suitable for both AC and DC, even at low currents.
Thank you.
It's nothing, but now I will need your help.
Let's hear it.
In the following, we will estimate the current consumption of the microcontroller, where CubeMX will help us out. Please open the .ioc file for the project and click on the Tools menu in the top right corner. By default, you will be presented with the PCC, which is the Power Consumption Calculator window. Here, among other things, you can set the energy profile of your device. You can specify how much time it spends in normal run mode and how much time it spends in one of the low power modes. In the drop-down menu found under Display Selection, you can choose the display modes, for example the time current graph and many more instructive charts. In the default sequence table, if you click twice on one of its elements, you can change the parameters of each sequence element. Here, you can also adjust which peripherals should receive a clock signal and which are supported in the sequence element. Close this window and go back to the left sidebar. Here you can set additional scoring factors. In the second point, you can see under which temperature conditions the calculated values apply. Higher temperatures are associated with higher consumption. In the sequence generator menu, you can easily play with the clock speed, runtime, and current values, as well as the combination of power modes. Especially useful is the immediate feedback from the development environment on the average power consumption and the computing power in DMIPS units. By the way, DMIPS, can you explain to the viewers the meaning of this unit of measurement?
I will try. DMIPS is short for 3 million instructions per second, a long-standing benchmark that measures how many millions of simple integer operations a processor can perform per second. It cycles through various algorithms and mathematical operations to give a clearer picture of the actual computing performance of the given device.
The main window returns the settings in graph form with additional calculated values below. The fourth section allows you to specify the power source for your microcontroller. If you select the battery option, you can choose from many types of batteries and even add your own. In addition, once you have selected the exact type, the sidebar shows valuable information about your chosen energy source. These are the source's capacity, self-discharge rate, nominal voltage, and the maximum amount of current it can supply continuously to the load.
Now that we have the basic hardware and software concepts to understand the topic, let's try them out in practice. Join us in the next video, where we will measure the current consumption of this panel. See you then, bye!
Bye!